Now, welcome to the second tutorial of ADAS 2020 and also the second time slot. And we have a fantastic tutorial in just a few minutes by Humberto, is joining us from Chile. And Humberto is online. I can see him. I'm in contact with him in Discord. And he will join us in just a few minutes. He's getting his computer ready, or he's set up, and things like that. While we wait, I will just do some Zoom administration stuff here, but I will be back in just a second. And, you know, if Humberto doesn't join exactly on time, I have very bad jokes ready. So we have somebody with the hand up, Rosa. Okay, that's our room manager. And I will get back. And there is Humberto. Humberto, you know, Humberto, I had a fantastic bad joke ready, but I will save it for the next tutorial. So Humberto, you're joining us from Chile. Is that right?
Yes, it's correct.
Awesome. What time is it over there?
8 o'clock in the morning.
Whoa. I hope you had a good coffee.
Yes.
Awesome. So Humberto, you're talking about from semantic segmentation to image instance segmentation using deep learning. I'm very excited about your tutorial. I see you're already sharing your screen, so I will let the stage for you, and I will get out of your way.
Thank you, Francesco. First, my name is Humberto Farias. I am from Chile. I am PhD candidate of University Santa Maria. Also, I will work in the Chilean Virtual Observatory. And also, I am part of the data science group in University of La Serena, also in Chile. Like the tutorial say, today we talk about deep learning applied to astronomy, especially in the task of semantic segmentation, classification and location, object detection, and instance segmentation. These are all tasks in computer vision, but applied with deep learning architectures. In the image that you see, I share first. I share the link of the notebook that you can follow me when I show the process to implement these networks. And the image that you see, these are the four main tasks in astronomy applied to the four main tasks of computer vision applied to astronomy. The first is classification. In this task, you have your input is an image, and you want to know if in that image you have a certain object. The second task is semantic segmentation, and semantic segmentation is given an image, can we classify each pixel as a belonging to a particular class? The second is object detection. Object detection is a more general case of the classification and location problem. In the real world setting, we don't know how many objects are in the images beforehand. So can we detect all the objects in the image and draw the bounding box around them? That is the main goal of this task. And finally, and the more powerful architectures are semantic segmentation, instance segmentation. And the goal of this task is, can we create a mask from each individual object in an image? Is different from semantic segmentation, because here we can have different instances of different class. For example, if we in this image we have two galaxies, but the galaxies are detected individually, are different from the semantic segmentation that we identify a galaxy in the general scope. But there is plenty architectures to apply to semantic segmentation. The more powerful and known is UNet. UNet is a full convolutional neural network. The reason behind why it is named a UNet is because of the shape of this architecture. The model, like you see in the image, the model looks in the shape of a U, and so the name has been derived from it. There is two main parts of the unit model. One part is the contraction path or the encoder, which is the left side of the model, and the other is the expansive path or the decoder, which is the right side of the model. You enter an image from the model, and we start with the contraction path. As a result, your data has been compressed in code in a few variables. From this higher representation, the network try to reconstruct the code, the input again. It is an end-to-end fully convolutional network. What is the meaning of this? This means that they only contain convolutional layers and does not contain a dense layer, because of which we can accept retraining and testing or images of any size. This is important because the traditional CNN or convolutional neural network have a finally output layer that is a dense layer that with, for example, activation function as a softmax to difference from, for example, this is a galaxy with 90%, for example, and the guys of unit don't have a dense layer, only because the goal is to segmentate or separate a certain galaxy or object from the background in the image. Like I say, the first part of the unit architecture is a set of convolution with a pooling that downsize the image resolution. Because of that, this is the name of the contraction block, and create additional layers to extract features from the original image. The contraction path, this consists of repeatedly applying two convolutional layers for three unpadded. The convolutional layer is followed by the activate the ReLU, the rectified linear activation function, and max pooling of 2 for 2 with a stride of 2, like we see in here. We start from the left side, we downside our image, we start, or we are encoded our image, and next we start with the decoder. It's also a network that takes the feature from a vector form to the encoder and gives the best closest match to the actual input or intended output. This is usually the same network structure that the encoder, the left side of the U, but in an opposite direction. We are a contraction path and expansion path in the right side. The expansion path consists of output convolution, the 2 for 2, also known convolutional transpose for upsampling. The up convolution reduce the feature map by the half. Later, the result is concatenated with the counterpart from the contraction path after cropping. Similar to the contraction path, the layer ReLU that is followed by, after two consecutive convolutional layers. And for example, here, for the intuition behind the model, given an input image, in this case, a galaxy, elliptical spiral galaxy. In this case, we have a RGB image of a galaxy. The UNet model produces a binary mass of ones and zeros, where 1 indicates a galaxy and 0 indicates a background, including in this the borders between the galaxy. Note that this is a semantic segmentation task because all the galaxies receive the same label of galaxy, because in this model that we work in this tutorial, we only want to separate a galaxy class from the background. And this is the general or the big picture, the general introduction to the unit. In the tutorial itself, the first thing we need to do is to check if we have activate the GPU support for our notebook. Like you see in the notebook, you need to go to the runtime here and enter to the change route time type. For example, I have the GPU support activate. You need to do the same in your notebook. And then we run the set, and we check that the notebook found a GPU at in this location. Second, we need to import our libraries to implement a simple version of UNet. We will use TensorFlow. We run this. And also we can check that we have one GPU available for our work. The next task we need to perform before we start to implement our model is to mounting the Google Drive locally. It's important we see that you can mount your Google Drive file by running this code. And we need to go to this URL to give the permission to our notebook to access our data. I select my account and go to, in my case, permitido, because it's in Spanish. We need to copy this code and put the code here and press enter. And now we are ready to use our drive space in Google for storage and process our model. We check that we have the access to our Google Drive. Yes, in my case, I can. Next, you need to create the folder for the tutorial in your drive. In my case, I think that I created before. Yes, yeah, I have created before. In your case, you don't have these methods. You can also check if you have the folder created in your drive access from the left panel and check here, drive, my drive, and the folder for the tutorial. In my case, I have more files because obviously I prepared this tutorial. Well, the overview of the all the deep learning models that or the life cycle to implement a model in deep learning follow these 6 steps. Before the first one is downloading and analyze the dataset. Second is prepare the datasets. And next, create the model, compile the model, fit to the model, and finally evaluate the model and the results over validation part of the dataset. The first thing we need to do is to download the datasets. This dataset has this form. We have a folder with the image. This is a JPA image from images and the spiral and elliptical galaxies. And also we have a directory with the mask. That is a PNG grayscale image. That is the ground truth or the segmentation to the correspondent image in the first folder. Because to train our model, we need to enter the image and also the mask to the network learn to generate automatically this segmentation mask. First, in my case, I will check I have the 2 folders. You need to download and comment this this command and run it. And now online again. Yes, we start again from the mounting my drive. And it's okay. And check if the files are correctly mounted. Yes. Next, we need to analyze our data set. The image has 3 channels, are RGB image that 266 for 266 pixels, and the PNG's mask only have a 1 channel because it's only 1 and zeros that has the form to the segmentation. We need to define the root directory path and that folders to access that folders. And this is our task to define the path to our dataset. We define the size of the data. You need this is a compressed version of our data, and also we have 3 channels because it's a RGB image. This is all the parameters you need to configure before the running the network. And need to sorting and compress the input to our model. And like you see, we have around 172 images. This is a toy data set because we have a limited capacity to perform the tutorial and collab. Obviously, you want to, for training any deep learning model, like you know, you need to have more examples of your data. Now we need to we check that our data has this form. For example, I have the original image, and this is a mask for the corresponding image. Is the same. This is important, obviously, because we need to enter the image and the corresponding mask for that image that for the unit learn the model. And for example, this is how I look our data. This is the original image, and this is the mask we we use as an input to our model. And in the case of the mask, we have only one channel. Next, we need to create the data loader class. This is because we use TensorFlow. If you use PyTorch, for example, you have a different data loader. But because we use TensorFlow, we use this class to read our data sets. We need to run this code. And right now we are start to define finally our architecture. The first step is to create the input. The input has the shape of the size of the image and also the three channels of the image. And it's okay. The three channels and the size of the image. Compressed like I said before. The contraction path is like I said before, is the goal of this path is to reduce the size of our image in the way to find to destacate the main features in the image. And we start the first part of the contraction part. And okay, this is all the verbose that the model show that when we create these layers. And next we have the filters, the three filters that that is we start with 64, 128, and so on. We run this code. It's okay.
So Humberto, I'll just interrupt you just a second. Do you want me to read the questions? There are a couple of questions.
Yeah, I read that they have the problem with the folder.
That's correct, yes.
I will check. Okay. Give me a second. I need to check my stream.
So just for everybody else watching on YouTube, there was an issue reported by a couple of people saying that in the downloads there were different folders or not exactly the correct folder. So Humberto is checking right now to make sure that everything is cool.
I need to check this. Okay, give me a second. I need to check this. I will continue before finishes. But I'm pretty sure that is the correct answer. I don't know. Well, we have also a class of using S3 from Amazon to upload, and it has the permission to access to the data. It's public. Okay. And how I send you the
If you want to send the links or even files, you can use the Discord channel tutorials.
okay.
That's the easiest option, I think.
Okay, I put the right URL in the Discord dataset, Discord tutorial. I will continue, but you need to the only difference is to change this for the new URL. Yeah, this is the correct folder. Yeah, I will continue. And we left here. Sorry for that, but in the next tutorial, we will use mass RCNN, and that dataset is for this part. I'm sorry for that. Okay, we are here in the unit create, and we finished to create the contraction path, and we need to create the expansion path. This part is the bottom part of the U when we pass to the expansion path. And like I said before, the right side is the same convolutional path, but in the different direction. Here we need to expand our data. And now to run the output, and finally create the model. The model is summarized here. And we can check. We have the contraction path from the bottom to here. We start the expansion path in the same size to the finally output. And we have the best approach to the same size of our image and the 3 channels, but with the segmentation mask. We need to split our dataset in testing and validation. And we have, because we have a little data, this is a dimension of our different datasets. Only because this is the goal of this tutorial is only present the architecture. You can work with your own data, and maybe in that scenario, and in that scenario, you need to increase the batch of size and also the number of inputs that you want you use to train your model. We configure our data, data training, deep learning training, and we start the training. This take a little because we have a GPU support, but only one GPU, and I think it's not a big one. And you start to train. Like I said before, this is this tutorial from the scope of the hyperparameters of the tanning, for example, the network, or use a different validation function or something like that is out of the scope of the tutorial. And obviously you can check for different activation functions or similar. But I only want to present the unit for the segmentation task to enter the second part of the tutorial that will use instance segmentation that is more powerful tool for perform the segmentation task. And we are finished our training. Obviously, we show the training and validation loss. It's very optimistic result, but maybe it's overfitting because we have a little data, and we need to we plot the the model to more and more visual representation, and we see the path to the constraint and the expansion path.
Humberto, there is
And
a question from one of your attendees, and it was wondering how did you build the ground truth images?
Yes, this is a very good question, because it's the one of the main challenge to train a segmentation model is to create the mask. In this case, I will use the second part of the tutorial, because this is part of a work that we present in astronomy and computing, and we implementate this model. I will talk in deep in the next stage part of the tutorial, but we use our implementation of mask RNCNN to create the mask. But you can use a different tools for computer vision and also things like that. But in this case, we use the ground truth using this architecture. And this is the output of the model. Only we create a code that for the creation of the unit data set, only take the segmentation mask, not the bounding box, and not the classification, and we use to create the data set. Okay. And we need to displace the, oh, sorry, I don't create here. Finally, we find the training of our model, and we need to test our network with the test dataset. It's the same dataset, but only the part for validation is. And we can show the results here. It's not impressive result because obviously only trained with 10 epochs, but you can see that this is the ground truth, and this start to take the form of the segmentation. Obviously, if I training the model with more epoch and more the more batch size, I will receive a better result. But this is only for the presentation of the unit, how to start with the contraction path and the expansion path, and what is the form of the data sets. The goal of this part of the tutorial is to show the basis of this approach. Obviously, here using a unit, there is a work performed, but I think the people from Carthage to hear this work, Morpheus. This is an excellent work using unit to perform semantic segmentation and also classification. If you want to check a very good work to use it, unit applied to morphological segmentation of galaxy, I strongly recommend to read this work. But the next part of the tutorial is focused in this. This is the more powerful deep learning tool applied to semantic segmentation, object detection, and instance segmentation. That is, say that I will segment this image and also that galaxy, but I will have a different identification for different instance of that class. This is a more powerful tool, and we start to show in this part of the tutorial.
Humberto, there is a question about some people getting resource exhausted error when training the model. Have you encountered something like that? And what could somebody do in that case?
I think that maybe is for the GPU support. Remember to perform this change runtime type. We need to check that we have the GPU support in our collab network, because that error is out of resources. Okay, this is the main part of the tutorial. I will talk more of this model, because I think that is a more powerful tool to perform a segmentation task, and also object localization, that is this bounding box over an object in an image, and also the instant the different to identify that is a certain pixel belongs to, for example, a galaxy. I think that this model need to have more application in astronomy. Well, the max RCNN is a state of the art of the region-based convolutional neural networks. The goal of RCNN family architecture is to solve the problem of object localization. This is the starting point. There is 4 architecture in this family before the max RCNN. The first one is RCNN, the second is fast RCNN, and finally faster RCNN, because to perform this task is a very computed expensive, and because of that the creator of this model work in the acceleration of the acceleration and also the accuracy to perform the object localization. To achieve this purpose, broadly speaking, the process is divided into generate the region of interest, or the proposal, and classify these ROIs. In the particular, finding the ROI present a highly computational complexity. In order to deal with this complexity and solve the problem, a series of architecture based on RCNN has been presented, like I said before. But the last one, like I said before, is the state of the art of this model is mass RCNN, and like we see in this diagram, the max RCNN, there is two stage in this architecture. The first is generate the proposals and about the region where may be an object based on the input of the image, and that is the region of interest. The second is predict the class of the object, that object, and refines the bounding box, and generate a mask in a pixel level of the object based on the first stage proposal. Both stages are connected to the backbone structure. Where is the backbone? It is a very important part of the architecture, Max RCNR architecture, and the backbone also is the first part of this architecture. It's a pre-trained convolutional neural network on an image classification task. For example, BGG, ResNet, the state of the art of classification using convolutional neural network. And it is called, this network is called the backbone because it's the word said is the backbone of the model, and it's the responsible to generate the space of feature or the feature map on the model. Here we can see the feature map of the architecture. Like, you know, the network, the convolutional neural network for classification task has a final layer, like the similar to unit, that not the similar to unit, the similar scope to take off the dense layer to perform the classification. In this case, we will remove the classification layer, the final layer, because we only need this network as a feature map generator. In this case, this is how what is the output of the model and the input for the next stage of the model. For example, we have this input, and this is the feature map that the convolutional neural network in the backbone generates, and it's the input of the next stage of the model. For example, here for the tutorial, we will use a ResNet, the residual deep neural network, ResNet, with 101 layers, and is pre-trained with we will use a transfer learning. The weights are for the work I talked before, that is pre-trained to classify and segmentate morphologically weight the galaxy. For example, here the feature map acts as input for the following stage of the model. In the feature, it shows the feature map that is at the backbone. It can be seen how different layers are sensitive after training with our dataset to astronomical objects in a different spatial scale. For example, we see this is a little galaxy or a little star here, and the main source in the middle. And here, this is we can summarize all the process or the stage in the mass RCNN architecture. It's shown by step procedure followed by the entire model being applied to a SDSS image. This is the output of the backbone. And next, we need to start with the RPNM. The RPNM is the next touch in the model. It's a region proposal network. RPN is a lightweight, fully convolutional neural network that operates as binary classifier. The process consists of running a small spatial window on the feature map generated by the backbone of image to generate a set of potential regions called region of interest. These proposed regions or proposals have different size because they depend on the size of the spatial slicing window used to generate them. The size of such slice windows defined an anchor box. This is all this is part of the configuration that we perform below to the notebook. And Decoder has many anchor boxes that have pertaining location and scales relative to the image. This is important because it depends of the problem we need to solve with this model. The size of the particular anchor boxes are closely related to the nature of the problem. In particular, for our work or for our tutorial, we will utilize anchor of size 4, 8, 16, 32, and 128 pixels. After the prediction or the boxes for the prediction are generated, in this case, we are talking about galaxies. And any model to aims to classify galaxies should consider they are different sizes because of, for instance, a Milky Way galaxy is 100,000 light years of diameter, approximately. And for other hand, galaxies such as M100 are approximately 52 million light years of diameter. Furthermore, galaxies will exceed a particular angular size according to their distance. Following this rationality, the size of the anchor that we use consider the size of the input of the image and the variety of the size of the galaxy, because you know they are in no astronomically speaking, only in the scope computer vision image, we have galaxies object the size of the half of the image, and we have galaxies that are small compared with that. Because of that, we need to parameterize these different slicing windows to to find the small objects and also the biggest one. The size answer that we use consider the size of the input and the image also, and the variety of the size of the galaxy that we can find in such an image. In particular, we chose a small answer considering the small size of the object in our sample dataset. The pixel scale is 260 for 260 is the size of the input image that you find in the dataset. Well, after generates here, after generate the boxes, the RPN generate answer are 3 different scales and 3 different aspect ratios. Each of these answer has a objectiveness-based score of 2 classes, object or not object. Finally, non-maximum suppression, NMS, is applied to the answer in order to remove the boxes that have not overlapped, because we want to the region with more overlapping. This is the goal. In practice, but this value is calculated using intersection over union metric, and the boxes that not reach a predefined threshold are removed. Intersection over union is a very common metrics in this kind of architecture. and measure the overlap between two boundaries. In EOU is the relation between the box that represent the correct position of an object, the ground truth, and another box that represent the prediction of the model for that part of the image. And this is the part that I are talking in this moment. And next, the RPN proposal that passed the binary classification process, object or not object, go to the next stage with the name of ROI, or region of interest. After applying no max suppression, there is a fewer answer than the number of candidates. This filter answer are renamed as a region of interest. And these ROIs, or region of interest, go through to two processes called ROI classification and bounding box regressor. The result of this process generate two outputs for each ROI: the class of the object and the bounding box for that object. The classifier, unlike to the RPM, incorporates the real class that the object belongs. In this case, whether it's an elliptical or a spiral galaxy. In the case of the bounding box regressor, it's necessary to make a size adjustment because the different size of the boxes generated by the RPM. This is the two states I talk right now. And also, the pixel level segmentation stage require much more fine-grained alignment with the bounding box. Therefore, it's necessary to obtain the fixed size of the boxes first. For this purpose, the model incorporates the stage called ROI alignment layer. The ROI alignment mechanism is based on cropping a part of the original feature map selected and bounding box and resizing into a fixed size. Here. And finally, of a very extensive process is indicated before, a unique element of the maths RCNN architecture for the object of this task is the ability to segment and also identify different instance of the particular class. The mask is generated by a full convolutional neural network receiving the input, the ROI selected by the ROI classifier. In other words, all the region that contain objects of the classes that exceed the minimum parametration accuracy, the threshold, and with a bounding box, of the defined size. This is the combination of these two parts of the model. One important aspect to consider for this model is the particularly that the astronomical sources do not exhibit sharp edges. In this sense, the mass are cheap to the pixel level and is represented as the floating numbers, achieving this more precision to do whether or not pixel belong to the classified object. This is relevant aspect for the automatical segmentation of astronomical sources generated by the model. The final result is verified for the classification, location, and segmentation of the in this case 3 galaxies. This process occurs with a single automatical pipeline based on a 1 deep learning model. this is the final statement for the max RCNN, because this architecture in one pipeline perform classification, object localization, and semantic segmentation. Because of that, I say that is one of the most powerful approaches to apply semantic segmentation or morphological classification of galaxies, for example. In the tutorial itself, the first thing we need to do is to define a particularly version of TensorFlow and Keras. We need to run this and install the requirements to setting up our environment.
Humberto, there is a question about
Okay.
how well does this model deal with overlapping or partially connected sources?
Oh, okay. Today the questions are the better one because that is like I said before, we have a work published, but that is that are working right now because in fact the case to show the result of our model, I only for I think that is not okay. In the final stage of the tutorial, the test case is to show the overlapping galaxy, but that is a more hard problem because it's very difficult to separate the galaxy. But we have a decent result right now. But I think that the best approach is also training the network and with this overlapping. We have the galaxy separate and also training with the overlapping. But it's a very good question that. Okay, I will continue because I will talk about that problem in the final part of the tutorial. Okay, in the first part of the tutorial, we use mounting our Google Drive, but in this part we use a different approach because in this case we programmatically modify the sharing settings of the data. We need to we programmatically create data, and Collab don't allow us perform that. Because of that, we use a traditional Linux approach to use Collab, because I don't know if you know, but Collab run over Ubuntu Linux. Because of that, we can use all the traditional Linux commands to perform or use in this tutorial. First, we go to the root or our root folder, not the root for the Collab. And in here, we need to create a folder called ADAS. And we need to clone, in this case, our implementation of the max RNCNN. Okay. And now we verify that the repository was cloned correctly. And it's okay. We have the model here. And we need to import the libraries. All this is to set the the root directory. We import our libraries. The principal are this one, the RCNN, the mass implementation. We check that we have the correct version of the Keras and TensorFlow. You need to have the same output here because the first part is to install this particular version. This is only for not showing the warning. We need this important install or import JSON because the dataset for mass is a different approach than the unit, and we will use a JSON file, and this is only for plotting the results. Like I said before, the dataset is different to the unit because we have separate the folder for training data and validation data. In both folders, we have image, JPH image, with 3 channels with any annotation, because the annotation is present in a JSON format, in a JSON file, in the COCO format. Because one of the considerations to use a convolutional neural networks in general is the need for training data set of the image able to satisfy the following 3 requirements. The first is the object in the data set have to contain a label indicating the class to which each object belongs. In this case, is a elliptical galaxy or a spiral galaxy. Second, the convolutional neural network require also to be equally represented in the dataset. And say in other words, we need to have balanced classes. Ideally, have the same number of example. This is all another problem or different techniques to achieve this problem. But in this case, we select a little number, the equal number of the spiral galaxy and the elliptical galaxy. This last requirement implies that the dataset needs to contain many images, usually several thousands of that. In the case of max RCNN, this is also necessary to incorporate an additional element of the mask. This last element is a key factor for the architecture because it provides the segmentation chip and implicitly the location of the objects. For do that, we use a tool called or a software called BGG for the annotation image, and also a code using a scikit-learn to generate a segmentation to train our model. And all this information is put in this file in via region data JSON. Now we need to clone, I hope, the correct dataset in our folder. We need to uncompress the data. This is okay. And this is the file that contains the segmentation mask and the label and all the information that the model needs. For example, here this is the name of the image, and this is for example, we say that the mass is a polygon, and all these are the points that define this mass. And the object is a spiral galaxy, the size of the object, and so on. If we have, for example, more galaxies in the same image, we have one definition for one object in one image. We need to define the path to this data, and we need to also for the data is that we will utilize in this tutorial. We use the labels is from the Galaxy Zoo, and the image are from SDSS, access to through the Sky Server web service. For each labeled object, we download an HGPA image center of the coordinates. And this is important, the weights, because we don't start from a black network or an empty network. Like I say in the first stage of the tutorial, we start with a pre-training convolutional neural network, in this case a ResNet, and the weight of this tutorial, we will use the weights of a pre-training network that we use in this work here. If you want to check it, I need to create the model. If you search in the web for other tutorials to the mass RCNN, all start from the COCO dataset. It is a very broadly used or known in deep learning applied to this task. But here we start with a network training to perform classification, galaxy morphological classification. We need to download the data sets, the weight of the network. Okay. And we need to define the path to the model and the weight. Here is the configuration to the network that has a lot of hyperparameters. The first, we need to define the number of GPU and the number of images that we pass for any GPU we have available. In this case, we have only GPU. Like I said before, we have a ResNet with 101 layers. We can also use a ResNet for 16 layers, or maybe use a BGG or another convolutional neural network using to classify images. And we have two classes because we have a spiral galaxy and elliptical galaxy. And also we need to incorporate a third class that is the background. Is always present in this approach. This is a threshold that defines the minimum detection content. For example, this is if in the training we find a galaxy or the detection with accuracy of 20% are excluded. Obviously, in the detection stage, we increase this threshold to 90%. But in this case, we use for training that parameters. The size of the image and the resize mode is the crop that we see in the more advanced in the tutorial. We define the RPM anchor that I'll talk in the first stage of the tutorial. And this is a very good approach, similar to the if you are working with, for example, tabular data and deep learning, you know you need to normalize that data, and in the way don't have points that escaped for the normal distribution. Similar approach is to have the mean of the pixels, and we find the length of the size of the data in the training and the data for validation, and the number of epochs and the number of validation steps. This is a very small, because this is the real approach is following that formula. Obviously, you want to use for your future work, if you want to use this architecture, because it is a fully operational architecture. If you change the data set to another data set, the network is continually working for your own project. You want to change these parameters, for example. And in this model, we use a ReLU, but like you know, right now are more advanced, maybe activation function like leaky ReLU, for example, or another in the family of ReLU activation. You can use that also. And this is an important parameter for performing or speed the training, but we see in the next part of the tutorial. We set the configuration, and it's worked correctly. Here's the configuration. This is for the showing the results. This is only for the notebook displays preference to define the size of the image that we show in the later part of the tutorial. Also, we have to define a data loader. In this case, we see we have one for a spiral galaxy, two for elliptical galaxy, and here are a commented tag. Before, like you know, and in Galaxies 2 there is a uncertain, but it's only to show that we can use many classes here. It's not a binary classifier, max RCNN. We can use any number of classes if we want. Here we define the subset, train and validation, the file that contains the segmentation mask and the label of the data. And here is the when we extract that data and put in the annotation format for the data. And this is part of the loading. You can read any details you want, but it is to load the mask from the JSON format. And now we need to lower the training dataset, and also load the validation dataset. Here we will show how the data is presented. This is important. For example, here we have a galaxy that we see the mass, but we see has incorporated another galaxy, and here is failing totally because not had the shape of the galaxy. But it's important because we use for this to prepare the mass traditional approach using scikit-learn, for example, something like that. But the model, the output in the model is very best in to generate the segmentation mask that we see in the tutorial, that the traditional method that we use to show the to prepare the data sets. This is the ground truth, for example. And the bounding box, here, this is only here is I will show you the part of the how we work in the practice, the hyperparameters of the network. One is the bounding box. This is the ground truth in this case. And later, that using the bounding box coordinates provided by the source dataset, we compute the bounding boxes from the mass instead. For example, with this, I say that in the JSON, there is a no field that say bounding box. We compute the mass over from the mass information. This is allows to handle bounding box consistently, regardless to the source dataset, and also make it easier to resize, rotate, or crop image because we simply generate the bounding box from the update mask rather than the computing bounding box transformation for each type of image transformation or data augmentation. This is very important because we do it in line, and depends only the mask. No, we don't need to recompute the bounding box and incorporate new information. And another important part, like I showing here, that is minimas here. This is solely for the speeding up the training. It's not a hyperparameter that depends on the theoretical model behind max RCNN. It's only for speeding up the model. And minimas. Minimas is a instance binary mask. We can get large when training higher. For example, if we the mask, the binary mask that is presented in the JSON file. For example, we have an image for more biggest image for 1024 for 1024 image, then the mask of a single instance require a 1 megabyte of memory for one image. If an image has a 1000 instance, then that we need to deal with 1000 megabytes for only one mask. To provide speeds, for example, here is the original mask present in the JSON file, and minimas is like what you see is similar, but is we optimize this with storage the mask pixels that are inside the object bounding box, not outside. For example, here for the mask, this is not present in the mask or the NumPy matrix that has the value for the mask. Rather that the masks are the full image, because all the points that are not in the bounding box are 0 because there is any object of that. And the most objects are small compared with the image size. And so we have a space that is not storing a lot of zero around the objects. We resize the mass to a smaller size for object, that the larger that the selected size, we lose a bit of accuracy, obviously, but most object annotations are not very accuracy to start. So this loss is negable for most practical purpose. And for example, the final layer mass after to this mini mass approach is very similar to the original. For the human, we need to maybe to make zoom to find difference, but this increase the speed of the inference and the training model. And I don't know what is the numbers exactly, but it's very powerful approach to increase the speed of the model. Well, finally, we need to create the model, and we read the folder where is the model, the weights to the model. Here we create the network in the training mode, because also have the inference mode that we see in here in the detection. And we will start training the network, but not including that only focus and training and here. We'll start training the backbone, but no this layer. Only using transfer learning to the capacity to generate the bounding box. All the other parts are training again. And here, this is because we read only the backbone capacity. We exclude the other part of the model to the generate the bounding box, the mass, and so on. And it's okay. And this is another important aspect to consider when you train this kind of model, because not always has the amount of data that you need to train this kind of model. Because of that, we use data augmentation. The training and validation data set are able to satisfy the need of the problem in terms of values, volumes, and the balanced representation of the examples for each class in this case, because we select that. As indicate the use of transfer learning based on the backbone of the network and the training strategy, we can provide a base knowledge to train the model. But also, as indicated in some works, the use of data augmentation helps to improve the ability to generalize the model. In data augmentation process, we will use ImageUt library. It has around 100 possible imaging augmenters and augmentation techniques, like you see here. These data augmentation techniques include affine transformation, perspective transformation, construct change, Gaussian noise, dropout of regions, hue saturation changes, cropping and padding, and so on. But in this case, to the galaxy morphological classification problem, not all the augmentation techniques have a scientific scientific relevance for the characteristic of the astronomical image. For example, maybe this technique don't have a pertinent or scientific correlation with the problem. Because of that, we need to select the correct the correct data augmentation pipeline applied to the dataset. In this case, we use 4 techniques. Or this pipeline consists in a sequence of 4 techniques: flip, flip for one side, flip out, one off. In this case, has a different 3 options. For one image, the augmentation techniques select one, and for other image, select another to rotate the image, because elliptical galaxy is presented in vertical position. If we rotate, it remains a spiral galaxy, and so on. Is intended to always perform exactly in one of the techniques that the group in this block, like I said before. And finally, we have the arithmetic technique called alt element wise, which aims to create new image by adding a slightly different pixel in the neighborhood. All of this is to create a new image from the original datasets. And here we have the training, and we have the a different parameters we need to configure. One important is the layers. We can train all the layers. That is the case, to fine tuning, to more has for example a learning rate more intense in the first layers, or in the last layers of the model, because, like in deep learning, the first layers of the model are dedicated to find the borders, or not the more advanced features, but the last layers are focused in that. For example, the difference between the final elliptical or the form. So, excuse me. And in this case, we chose a traditional learning rate, a very template learning rate, and also we perform a fine tuning over all the data. But in this case, I will don't run it. If you want, run and wait for 1 hour or 2 hours to finally to training the model. But the correct you need to see eventually is here when start the training. I will not do that in this moment, because the tutorial is finished. But we have the when you the training finish, you need to storage your model, or the weight of your model in that way. And here it is the same. We start to reading finally. This is the part of training, and the part of the detection part. We need to are the same. We start to the folder, but in this case, like I know not restart the environment is not necessary. I go directly to the inference mode. In this case, we need to create an inference stage of the model different to the training mode. In this case, we define one GPU, one image per GPU, and the threshold of the detection confidence. That is the model. Don't focus in any galaxy that the accuracy is lower than the 90%. And we configure it. And now we are running, sorry, load the weight, this weight, and it's okay. This is the same. All this is you run this and you say, oh, I don't wait for finish. I will restart the kernel. We run the same configuration to lower the library. Because of that, I put here if you want to restart from here. Maybe this is another notebook if you want, but this is all the steps you need to perform if you want to detect image. No, it's not necessary to perform all the stage upper from here. Is here. I need to read the validation dataset. And this is for the visualization. Import datetime. Select one image for the validation dataset. And this is the ground truth. This is that we present to the network. For example, is this model, this image is used for training, but is not part of the training dataset. It's part of the validation dataset. And the goal, obviously, is to do better than this. We need to define the name of the model. And we perform the detection. This take a little. Maybe if you later you load the notebook and you run it in Amazon Web Services, or maybe in your computer with a GPU, this will run very fast. But here it's running slow because the computer support we have, but eventually it will finish. I need to wait for a little. And here, this is finally the result of the model. And we see, in this case, had a segmentation. And finally, this is, if you want to perform this for the final preparation of your data, for example, you create your model to select to find, for example, pulsars or galaxy with especially characteristic, and you need to present your result to a reviewer. You need to calculate the final accuracy or result, and the map is that you use. Here you need to put the size of all your data in validation and run it and obtain that result and put in your paper. And this is the finish of the tutorial. This it will finish in a few moments, and we see Patty set a toy example because I only put 10 images to calculate the map and to compute the precision of the model. But this is all I want to show you today. I see there is a question. Okay, I see there's a question. Yes, it's because these model depend on NVIDIA support.
So the question was whether you can run this model on your laptop. And actually, I had a similar question myself. You know, suppose I wanted to run this type of models on you know my image data or whatever locally. And what would be your suggestion? I mean, I guess a laptop will not quite be enough. So would you suggest setting up a server with a GPU or more, maybe than one GPU?
Yes, but maybe a laptop is enough, but depends what you have in the laptop. For example, I can train in the model in my laptop because I have a Mac and I don't have a NVIDIA GPU support. Because of that, I use Amazon Web Service, and I upload my data similar to the workshop here to S3, and in fact, I will show you where I training my models. And this is the AC2 machines for deep learning, and you can choose in this case the number of the GPU you want in your model, but it depends on the size of your data. For example, for training the model that is in the paper, we for only one version of our network takes 5 hours to train all the data, but we use this network. This has 8 GPUs, and obviously this is stopped because Amazon is you pay for the use in Amazon. In this case, I always is retained, but when I want to train the model, I start the machine and connect to the machine and training my model.
Wow, 8 GPUs.
Yeah,
that's quite something. Look, there are also 2 other questions. So have you tried with more efficient networks like MobileNet version 2 or EfficientNet models?
yes, in the fact, this is a spoiler because I have a poster in others that in that case to increase the speed of the inference we use a BGE, but we compress the size of the nodes of the neurons, pardon. Because one of the principal complexity of the network is the number of parameters that need to calculate in any stage. Because of that, we use a tensor decomposition method. This is similar to PCA or SVD or in general matrix factorization, but apply it to a more general or more dimensional space. And we achieve an increase of speed on 2%, or we reduce to the half the time to perform the inference and the training, but using that technique. But obviously you can change the backbone for any classification convolutional network, neural network that only you need to the network has the ability to create the feature map.
Okay, wow. There are a few more comments and questions. One was, suppose you don't have access to a GPU, maybe because you, well, for whatever the reason. Will the model run at all on something without a GPU? Or does it need, in this particular case, a GPU, you know, to run at all?
The answer has two answers. For training, you need a GPU. That, in fact, is the reason because we don't have deep learning in the past. Because in the past, because I don't know if you know, but the deep learning of the convolutional neural network are invented in the 80s, but we don't use that models because we don't have the computational support to perform, for example, the convolution. Because of that, we need to GPU for training. But for inference, you can use a CPU because you download your weights and you can run in a CPU.
Okay, fantastic. One more question. How much data was used to train the model? And what were the critical elements in the data set to get good results?
Yeah, the data sets that we use for the task in the paper, we used 24,000 of images. There is many aspects that we incorporate in that work. For example, we only use the brightest galaxies in the image, and we center the image. We use like I say a sticker because we have only galaxy in the center, but the network works in a big plane and find the galaxy. And but if you want to speak in general terms to prepare to data set for deep learning, you need to take care of the number of images, and you need to have a balance in the class. For example, you have 10 elliptical galaxies, you need to 10 spiral galaxies, but there is a techniques, for example, that you have punish the class with more examples, and you can increase artificially the weight of the class that is less represented, for example. This is one approach also. But it's very important to the class are equally represented because if you don't have that, the model learn to more a lot of more in the fact to the class are more dominant. And there is and other aspects like in this case we want to improve is when we generate the ground truth. Like I select the worst case because I want to see that the traditional techniques, for example, to automatically generate the ground truth, they are not very accurate. And because of that, in many cases in deep learning, the annotation is performed by humans using a, a web service tool. You upload your image and you manually generate the mask. Because of that, we want to use a unit to generate the mask and then train the mask RCNN.
Okay, fantastic. So could this tool be used to identify H2 region in the individual galaxies, even if they are indeed overlapping, for instance? Christoph is asking.
Yeah, that is the question that another person asked me before. But in this moment, we don't have the ability to perform the overlapping segmentation with accuracy in this moment. But we applying to the galaxy morphological segmentation. But in the real problems day-to-day classification, for example, I have a car here, I have a car before, that is solved. But what is the main difference? Because in the real world are shapes, for example, and the galaxy are very soft, and that is one of the biggest problem to achieve that overlapping classification. We are working in some approaches to achieve that, but in this moment it's an open problem.
Okay, some more question. Is there a possibility to add another regression head to the network? For example, for predicting the viewing angle of a galaxy? And is that something that can be done?
I don't try that. This is a very interesting idea, but in this moment I don't work on that. But you always remember that we can use a model, a standalone model, for example, like here. But always you can create an ensemble of models, for example, we want to do now. For example, use unit to create the input to the max RCNN. Maybe you can add a stage between the feature map and the right alignment and put another network that performs that task that you are commented before the classification and bounding box and the segmentation. I think that maybe work. Very optimistically, but I think maybe work.
And another question. The algorithm is affected heavily by noise and resolution.
Yeah, that is a very good question because I don't refer that in my talk, but in generally the convolutional neural approach to the instance segmentation of object localization is very responsive to support the different, for example, in noises. In the paper, we artificially incorporate a Gaussian noise to the image systematically, and in the fact there was an endpoint that is ridiculous, but the network continually identified the galaxy, but obviously the accuracy is slowing, but for noise it's very don't affect too much, but the size is a different kind of problem. Because if you remember the first part of the talk, I talked a lot about the size of the anchor. And because of that, if we have a very big, say another word, you need to train your model in taking in the mind what will be the final application of that model that you are training. If you train the model to find galaxies in a certain sizes, you put that sizes in the model, because if you don't put, it's very probably that the network don't see, for example, the biggest one galaxy, for example, that cover all the image, or the little ones. That is, I think, the answer to that question.
Awesome. Well, Humberto, thank you so much for your tutorial. The next one will start in exactly 5 minutes. We know that preparing these tutorials is a lot of work, and we are really grateful that you spent the time and you work hard to deliver a great tutorial. And we are all very, very grateful. I found it very interesting. I learned a lot from this tutorial as well. I also learned that I have to buy some GPUs, but okay, that's life. And so we would really like to thank you again. And folks, for everybody else, the next one, Peter's tutorial starts in 5 minutes. You can keep discussing with Humberto on Discord, and you can use this 4 or 5 minutes to get another coffee, or eat something, or whatever, run to the bathroom, whatever, and then we will start with Peter. Humberto, thank you so much. Thank you.
Thank you for the invitation.